Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a final video on plane curves and parametric equations for a trig course or pre-calc, just depends on what course you're in, or you could be reviewing it because you're in Calc 2 and you need to review all of parametrics. That does happen as well. So all these are meant to help you. In this video, we're going to focus on the parametric forms of polar curves. So at this point, you should have already covered all of trigonometry. You should know what polar curves are, or what a polar function is, right? So polar equation R equals some function of theta. And now we are going to transform that polar equation into a parametric curve, or a parametric set of parametric equations. Turns out that polar equations are naturally parametric equations. And the way that you can do the transformation is fairly easy. You just have to remember basically two things. X is always R cosine of theta, and Y is always R sine of theta. If that's the case, and somebody said, oh, I have a polar curve, and the polar curve is R is equal to some function of theta, well then, X is equal to that function of theta, cosine of theta, and Y is equal to that function of theta, sine of theta. And generally when you're dealing with parametrics, you just trade out thetas for t's. And so here we have it right here. X is your R function of t, cosine of t. Y is your R function of t, sine of t. I didn't call it R down here because, well, we defined it to be R of equals f of theta, so I just called it f of theta, but you can call that R of theta if you want. So seeing this in action is actually as easy as the theorem. Express the polar equation in parametric form and then graph it using technology. Okay, so I know that in parametric form, X is always R cosine of theta. Well, no, not in parametric form, but in polars, the X value is R cosine of theta. So instead of thetas though, I'm going to use t's, just because we're going to switch over to parametrics. And remember, R is also a function of t. So I'm going to go ahead and say it this way. R of t cosine of t. You might say, wait a second, R looks to be like a function of theta. The reality is a letter is a letter is a letter. You could call that R equals 2 raised to the happy face over 12 for all I care. As long as you're consistent with that variable, it's not that big of a deal. So with parametrics, we use t almost always as our independent variable. So I'm just transitioning from theta to t. There's no big, all it is just rewriting it. So let's see. What is R? Well, R is this guy right here. So it's 2 raised to the t over 2 power, t over 12 power, and then cosine of t. That was supposed to be a t, sorry about that. And then Y is R sine of t. Again, that's from polar coordinates. But remember, R, according to this up above, is just a function of t, or theta, but I'm calling it t now. And then we know from polars, again, Y is defined to be R sine of t. So we get R of t sine of t, but R of t was 2 to the t over 12 sine of t. And so there are our polar equations. X equals 2 raised to the t over 12 cosine of t, and Y is equal to 2 to the t over 12 sine of t. And we're going to graph that using technology from t is equal to 0 to t is equal to 4 pi. So here we are in Desmos. I'm going to go over here and just plot that point. Now, you could call it f of t, by the way. I could say our x value, f of t, is equal to 2 raised to the t over 12 cosine of t And our y value, g of t, is what we usually reserve for that, is equal to 2 raised to the t over 12 and then sine of t. Obviously, these are the Cartesian graphs. I don't want those, so I'm going to turn those off so I don't see them. And I'm just going to graph f of t versus g of t. And again, we wanted to do that from 0 to 4 pi. And you get this beautiful spiral. That's all it is. And if you want to go further, you totally can. You can go to 8 pi. It's just a bigger spiral. So there you go. Very fast. Let's just do one last example. We're going to graph r is equal to a sine of theta over theta, but we're going to graph this using the parametric form. This is the polar form right here. So r, notice, is a function of theta, and it's equal to some parameter times the sine of theta over theta. But what I'm going to do is trade out that theta for t's. R of t is equal to a sine of t over t, just because I'm going to move into parametric form. In parametric form, well, maybe I should say in polars, x is always defined to be r cosine of theta, but we're going to use t here. R is a sine of t over t, and then we have this cos of theta, or cos of t, sorry. And then y, again in polars, is always r sine of t, but that's going to be r is a sine of t over t, and then we're multiplying that by a sine of t, or basically you have a sine of t squared. Let's go ahead and see what that looks like in Desmos. Something I want to mention before I start graphing this is that when you're doing a sine squared or cosine squared in Desmos, it does not accept the notation with the exponent between the n and the parentheses. So I have to make a group called sine and square that group. That's just a little side note there. Anyhow, let's go ahead and graph f of t versus g of t. And let me change my, well, no, I won't change the a values, but I'll definitely increase the time value. Let's just go to time equals 10 to see what that looks like. Well, zooming in, I think it'd be nice, right? Let's go to time equals 100. Ooh, wait, hold on a second. Oh, wow, that's really pretty. You can tell I'm easily impressed, aren't I? And let's see what happens when we change that parameter a. So I'm going to increase a. Oh, it just widens it out. Okay. So, and then decrease a, it flips it upside down. Okay. So there we go. That's a good, fun little graph. It's like a sunrise graph or something like that. I have no idea, but very, very pretty. And if you put it to 1,000, it goes deeper in, right? It's a deeper dive. You can almost break Desmos with one of these things because Desmos can't keep up with the computation after a while. But very, very pretty stuff here. All right. And you can see it's actually taking form here. So that's kind of neat. Okay, so that's it for this video. And that's actually it for all of parametrics. There's, again, they're very, very powerful in calculus. I'm just seeing if this will become resolved. Oh, it does. How neat is that? They're very, very, very important in calculus, but it starts only halfway through Calc 2, maybe towards the end of Calc 2, and then all throughout Calc 3.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.